All right, let's dive into cracking the code of advanced organic chemistry. I know, naming these big, complicated molecules can feel like you're trying to learn a secret language, but I promise you, by the end of this, you are going to be fluent. So let's get right into it. Okay, just look at this thing. Seriously. If your first thought is, whoa, where do I even begin with that? You are definitely not alone. It looks impossibly complex, right? But believe me, there is a clear, even kind of beautiful logic hidden inside all that chaos, and we're going to pull it apart together. So where do we start? Well, every single one of these names, no matter how long and scary they look, is built on a really simple foundation. Let's just push all that craziness aside for a moment and focus on the basic rules that bring order to everything. These 4 rules, this is your foundation. This is everything. First, you got to find the boss, the most important functional group. For instance, you see that COOH group? That's your #1 priority, for sure. Second, you find the longest carbon chain that boss group is attached to. Third, you number the carbons in that chain, but you have to give the boss the lowest number possible. And finally, you name and number all the little side groups, the substituents, and you put them in alphabetical order. That's the playbook. Okay, so you've got the basics down. But what happens when the molecule gets, well, a little greedy? What if instead of just one boss acid group, you've got 2 of them? This is where things get really interesting, and where chemists came up with some pretty clever, tricky shortcuts. Now here's the crucial part. A molecule with 2 carbons and 2 acid groups has a super formal IUPAC name, ethanedioic acid, but almost nobody, and I mean nobody, actually uses it. It's like the formal name on your birth certificate that you never go by. In the lab, in conversation, and most importantly on your exams, everyone calls it by its common name, oxalic acid. And yeah, there's a whole family of these things with common names you just kind of have to know. Trying to memorize a random list of names is, well, it's a nightmare. So for generations, chemistry students have used this amazing little mnemonic to keep them all straight. You just have to remember the phrase, "Oh, my son, go and pre." It sounds totally random, I get it, but trust me, this is the key that unlocks all of those names in a snap. So here's how it works. It's brilliant. Each word stands for an acid. O is for oxalic, which has 0 CH2 groups squished between the 2 acid heads. Mi is for malonic, with 1 CH2. Sun for succinic with 2, go for glutaric with 3. You see the pattern? It goes right down the line. So this trick doesn't just give you the name, it literally tells you the structure of the molecule. This is an absolute game changer for exams. All right, on to the next puzzle, the CN group. You know, this group has a total split personality. Depending on where it is and what its job is in the molecule, it gets one of 2 completely different names. So how do you know which one to use? Okay. Here's the breakdown. If the CN group is just a little side attachment, a substituent, we treat the whole CN unit together and we call it cyano. Simple enough. But if it's the main highest priority group, the star of the show, something really cool happens. Its carbon atom basically gets a promotion and joins the main carbon chain, leaving the nitrogen all by itself. And in that case, we call it a nitrile. I absolutely love this way of thinking about it. When the CN group becomes the boss, its carbon sees a better opportunity. It's like it thinks, hey, I'm a carbon, I belong with the other carbons in the main chain, and it just abandons the nitrogen to go join them. That lonely nitrogen left behind is what gives us the name nitrile. See, a little bit of molecular drama helps you remember the rule. All right, let's tackle another special case, amides. Specifically, what do you do when you have groups attached not to the carbon chain, but straight onto the nitrogen atom itself? Yep, you guessed it, there's a special little naming rule just for this. So real quick, what's an amide again? It's just a functional group where you have a carbonyl, that's a carbon double bonded to an oxygen, and it's linked directly to a nitrogen atom. The most basic form is CONH2, but those 2 hydrogens on the nitrogen, they're the key because they can be swapped out. And here is the special rule. When a substituent, like a methyl group, is hanging off the nitrogen atom instead of the carbon chain, we can't use a number, right, because the nitrogen isn't part of the numbered chain, so instead, we use the prefix N-. So if you have a methyl group on the nitrogen of a butanamide, you wouldn't call it 1-methyl something, you'd call it N-methylbutanamide. It's a really simple, clever way to tell everyone exactly where that group is. You know, we've just covered some really specific, kind of tricky rules, And it's so easy to feel overwhelmed by all these details. But I want to just pause for a second, because mastering organic chemistry isn't really about having some special talent for it. It's about something way more fundamental. Just let that sink in for a minute. It's so easy to look at other people and think, wow, they're just getting this so much faster than me. But what truly matters is persistence. It's about grinding through those practice problems until the rules just click and become second nature. That effort, that's what guarantees you'll get this. So don't worry about comparing yourself to others. Just commit to doing the work. Okay, pep talk over. You've seen the rules, you've learned the tricks, you understand the logic. We've been building up your chemistry toolkit piece by piece. So now it's your turn to be the code cracker. So here it is, your naming toolkit. Number 1, always find the boss functional group first. That's your anchor. 2, if you see 2 acid groups, use the oh my son mnemonic. 3, if you see a CN group, you've got to ask, is it just a cyano side group, or is it the main nitrile? And 4, for amides, always be on the lookout for those N substituents. These are your essential tools. And so we end right back where we started. But this molecule doesn't look quite so intimidating anymore, does it? You're not looking at a mess of lines anymore. You're looking at a puzzle. And you now have the fundamental logic and all the tools you need to start solving it. The question is no longer, where do I even start? It's, okay,